perhaps the most striking thing about this second degree equation is just the size of the coefficients, and also noting that they're odd. Now I'm going to make a quick statement right here. If you sum up three odd numbers, and let me just write this down in this form. 2k sub 1 plus 1, that's an odd number if k sub 1 is an integer. And then let's add it up to 2k sub 2 plus 1. So I'm going to sum three odd integers, state something that's fairly obvious, and note that this is looking that way because the coefficients are odd. They're large and they're odd, okay? And also note that any zeros, any integer solutions would have to be odd because they would have to be a divisor of this odd constant term, and you can't have any even divisors because otherwise it would be an even number, right? So any divisor of 549,585 is necessarily odd because if there was an even divisor, the number would be even, which it's not, of course, manifestly. All right, now, so let's write down, let's finish this up. Because this turns out to be the proof, basically. There's just a few more things to say after this. Now notice that this will end up being equal to 2 times the quantity k sub 1 plus k sub 2 plus k sub 3. And of course, you know what I'm going to do, folks? Notice how there's a 3 here. So I'm going to go ahead and put plus 1 right here. You could write it either way, and then I'm going to go plus 1 over here, right? So do you agree this is, because you see you have 1 plus 1 plus 1 is 3, right? So I just chunked one of them into here. And so what we have is this is definitely an odd number, right? Independent of the values of k sub 1, k sub 2, k sub 3, this is odd. Okay, and more importantly, not equal to 0, right? And this is almost the proof right here. This is almost the proof. Now let's go down and just finish it off. By the rational zero theorem, and I referenced this earlier, any root r has to be a divisor of the constant term, and that implies r is odd, right? R could not be even, otherwise the constant term would be even since it has an even divisor, right? So that's very, very clear. So let's continue on here. And I just stated something that's true, but let's just go ahead and write in r squared. R squared would be, if r squared was a 0, okay, r has to be odd, right? We've just shown that. So you would have r squared plus ar. And remember, a and b are odd integers. That's the more general truth here. Plus b, okay, is odd, right? Meaning it can't be equal to 0. Okay, so I'll put not, well, I mean, this is odd. That means it can't be equal to 0, and we just said that. So this is QED time. And I like this because if you were to look at this, you might be tempted just to start checking these integers, divisors. And y'all, you'd have to write down the prime factorization of 549,585. But I think there's about 40 divisors here. I can't quite remember. Don't hold me to that. But I think there's 40 divisors. So you'd be stuck checking 40 divisors using synthetic division or something like that. But if you just take advantage of the fact that these large coefficients are odd numbers, and then you have the more general truth here, you see, the more general truth, if a and b are odd, then this has no integer, this equation has no integer solutions by our earlier argument. Okay, so in other words, this is a nice example of looking at a special case with large coefficients, and then just proving something more general that fits this thing, no matter what the size of these odd numbers are. Okay, but this is the part I like the most right here, is that just the sum of any 3 odd integers, whether they're consecutive or not, cannot be equal to 0. You're always going to have at least a 1 left over, depending on, and most of the time it'll be something, but it's not going to be equal to 0. That's a fact. And that's really the kind of the basis of the proof, along with the very well-known rational zero theorem, which applies to any polynomial with integer coefficients. Okay? So anyway, we're done, folks, and thanks for viewing.